When Thomson discovered the electron, he was only able to measure the charge-to-mass ratio, but not the separate values of the charge or the mass of the electron. About 10 years after this discovery, the charge of the electron was finally measured. It was measured using something called the oil drop experiments. And this was done around in the year 1909 by Robert Millikan, Millikan. So we often call this the Millikan's oil drop experiment. Let's see how it was done. Right, in this method, there are two parallel plates. Again, now this the top plate is positive and the lower plate is negative. Let me make some more space for them. Okay, top plate, I have a lower plate, and the top plate is positive. The lower plate is negative. And the method is this. There is a little tube. From this little tube, some little droplets of oil is sprayed. This oil is sprayed to this space between the plates. So you get lots of tiny droplets of oil floating around. Okay. Now these droplets are tiny. They must be of the size of micrometers. So they're actually very hard to see. Now to make it easier, to make it possible to see these little droplets, requires a very bright light. So there's a very bright lamp shining at this space between the plates. And if you look at the droplet under this bright light, each droplet will appear as a very bright spot. Tiny but a bright spot that you can see. Okay, so we are actually able to see the droplets. And the idea about the spraying is this spraying process means that there would be friction between, say, the oil and this little tube there that holds the oil. Okay, there's probably some spray can behind this. So we know from static electricity that if you have friction between two things, you can get static electricity. And in this case, the droplets of oil can gain some negative charge. Okay, so we are hoping that the oil droplets has some negative charges attached to them, some negative electrons. Now, but we won't actually know this. I'll draw the droplets a little bit bigger. Now we won't actually know how many electrons would be on each droplet, even if that there are actually electrons. We would know how many electrons there actually would be. So that's a problem. Okay, and we'll talk about how to sort this out later. But for now, the first step in this experiment is to measure the charge in each droplet. We don't know how many electrons there are, but let's try and measure the charge first. Anyway, we'll worry about the number of electrons later. So let's think about how we might measure the charge of a droplet. Okay. Let's say I'll just look at that droplet there, and let's say the charge of the droplet is Q. Okay. Now the electric field between the plates would produce a force. An upward force. And that would be equal to the charge times the electric field strength, E. And there is another force, of course. There is the force of gravity acting downwards, mg. So we have two forces, one up and down. And the idea behind this oil drop experiment is that we would need to adjust the voltage between the two plates and thereby adjust the electric field strength until the electric force just balances the weight. So that if we look at the droplet, it would become at rest. It would just hang there, suspended in mid-air. Okay. And it is a difficult experiment, needs a lot of patience. There are so many droplets, and you need to just pick one and squint really hard, maybe through a microscope or a telescope. You need to just focus your eye on one drop that is sort of moving, drifting slowly, and then adjust the electric field until it stops moving. It stops going up or coming down. It might still drift sideways a bit. Okay, so it's very tedious, but it can be done, and it has been done. 1909 by Robert Millikan, and today probably at universities as part of undergraduate practical experiments. Okay, so let's try some example values to get a better idea about how this charge could actually be measured. Okay. Now we'll use these two forces to guide us along the way. So let me start by saying that when these two forces are balanced, the oil drop will hang in the air, it won't move. And in this situation, we would expect that QE, the electric force, is exactly equal to mg, the weight. And therefore, if I know E, m, and g, I should be able to solve for the charge. So let's look at this one by one. Okay, G, we know G is 9.81 meters per second squared. That's fine. E, we would know. E is given by this formula. I'll call that, let's say the voltage across here is V1, which is a Okay, and let's say I need to adjust this to 10,000 volts when one of the droplets stops moving. Okay, let's say that's the voltage needed to balance the weight of one of the droplets. And suppose that the spacing in between the plates is 1 centimeter. So therefore, okay, if I represent this by D, therefore the electric field is equal to the voltage over D. So this allows us to find E. So we would know E as well, once we know the voltage and the distance, which can be both can be measured. So that's not a problem. The tricky bit actually is the mass. Now we can't exactly, plug this oil drop out and put it on a weighing scale and weigh it. This oil drop is tiny, like I said, maybe micrometers. So the moment you touch it, it will just stick to maybe your finger, and you can't find it anymore. So how do we find the mass of this? Now we can find the mass of this if we know the density of the oil. That's not a problem. You can just weigh a large amount of it. But the volume, knowing the volume will be tricky. It's such a tiny droplet. How do we know the volume? We might imagine putting a very powerful microscope next to this setup and try to measure its size. That might work. But what was the method that was used by Millikan was very clever. He did not use a microscope. What he did was to switch off after finding this voltage that balances the drop. So switch off that voltage and allow the oil drop to fall. Now when the oil drop falls, because it's so light, it very quickly reaches terminal velocity. And there is a formula that relates the terminal velocity to its radius and its force. Now I shan't go into detail of that, but I will just assume that it has been done. It can be done, and let's say it has been done, so that we for this example, I'll think of it as just a separate method that Millikan and maybe his assistant would have used to measure the radius of this droplet. So suppose that is done, that is measured, and the radius was found to be 1.695 micrometer. Okay, that's the radius of that tiny droplet there. And suppose that the density of the oil has been measured separately, the density, and that was 0.8 grams per cm cubed. So once we have this, we have enough information to calculate the mass. Okay, because let me just write this out. Because the mass would be density times volume, and volume would be 4/3 pi r cubed, the volume of a sphere. Okay, so therefore, once we know the radius, we know the volume, and once we know the density, we know the mass. So we would know all of these numbers. Okay. So putting all these into the equation, we can solve for Q. So for Q, the charge is equal to mg over electric field strength. Just rearrange that. And that. Okay, is equal to m is density times volume. To G there. And E is actually V1 over D. So if I put it in here, we're dividing by V1 over D, and that gives us times D over V1. Okay, so Q is equal to, and V is this, so rho times 4 over 3 pi r cubed times G times D over V1. And if you put in all these numbers, rho is this. Remember to convert this to kilogram per meter cubed. Okay, and R is this. Remember to convert micrometer to meters before substituting it into here. G 9.81, V1 10,000, D, what is D? D is 1 cm. Again, convert to 0.01 meter. So putting all the numbers into here, if I use my calculator, I would find 1.6 times 10 to the minus 19 per coulomb. Now, if you have remembered the charge of an electron, you'll know that this just happens to be the charge of the electron. Okay. So these are numbers that have been chosen in this example that would give this value. So what Robert Millikan might have measured, right, would almost definitely not be exactly this value. There would be there could be some difference because of measurement error, errors in measuring voltages, distances, and so on. And more likely, the oil drop would have a few electrons rather than just the one. So he might have measured other values. And indeed, he did. He measured the charges on many droplets, and he got many values. So let's just take a look at what he might have got for his measurements. Just call this. Okay, so in Millikan's measurement, suppose that the charge that he measured, let's see, let me write down some possible example values. I'm going to give this charge in units of 10 to the minus 19 coulomb. Right. So we know that the charge of the electron is 1.6. So perhaps one of the oil drops has just one electron, but he would also have obtained other values. Just for example, he would have observed, say, 6.4. He might have observed 4.8. He might have observed 3.2. And maybe slightly different values, right, around each of this. So he would have observed all of these values and more. So how did he know? How would he know? How would we know, looking at these numbers, what is the charge of an electron? You might look at this and say, it's the smallest one. Okay, but that one, because it's so that's one way of doing it. But we have to remember one thing. At that time, during the very early times of the turn of the 20th century, very little was known about electrons apart from what Thomson has discovered some years earlier, and it was not even known that that electric charges have to be in units of the electron charge. For example, can we not have half the charge of an electron, or can we not have just any charge we want, right? Because people did not know about electrons, and this has never been measured before. So from that point of view, these numbers actually turn out to be to provide a very important information. What happened was that by analyzing these numbers, it became clear that all of these numbers are multiples of 1.6. So 6.4 is actually equal to 4 times of 1.6. 1.6 is 1 times 1.6. 4.8 is 3 times 1.6. 3.2 is 2 times 1.6, and so on. So it's always, for all the charges that were observed of the droplet, there are always some whole number times 1.6. Now this in itself was interesting and also surprising, because there's no reason to think at that time, when people actually don't know much or anything about electron, there's simply no reason to think why it can't be like 1.7, 1.8. What's wrong with that? But this was what was observed. So this very clear experiment shows that electric charge has to be in units of this 1.6 times 10 to the minus 19 coulomb. Can't be anywhere in between. You can't have a fraction of this 1.6 times 10 to the minus 19 coulomb. Now this observation and this property, that electrical charge can only happen in these multiples of a single number, in these fixed definite steps, has a name, has this name to describe it. It is called charge quantization. It just means that the charge can only occur in steps. In steps of values. Okay, either 1 times 1.6, 2 times 1.6, and so on. You can have 1.5 times 1.6, for example, or you can't just have any value you like. And so what Millikan actually observed was charge quantization, and that you can have zero charge, of course, but if you have a charge, the smallest charge you can have is 1.6 times 10 to the minus 19 coulomb. And actually, there's no reason, just from this experiment, to expect that this 1.6 is the same charge, is the charge of the same electron that was observed in Thomson's experiment. After all, these are oil droplets, and Thomson was using a metal cathode with a vacuum, so it's a completely different situation, right? So it takes a big jump in imagination to associate this 1.6 charge with Thomson's experiment and say that they are the same, that this charge is actually the charge of a single electron, and these numbers just mean different number of electrons on the droplet. So this interpretation that these are charges of electrons requires a jump, a leap in the imagination. And it turns out to be right and confirmed because it's confirmed by new experiments as the years go by. So with this value, let me just, before I leave this topic, let me just complete the picture by calculating the mass of the electron. Okay, so the result here is that the charge of the electron Q, which from now on I shall call it E, charge of the electron, is 1.6 times 10 to the minus 19 coulomb. Okay, and we know from Thomson's measurement, I use E over ME now instead of Q over ME. We know that the charge to mass ratio is 1.758 times 10 to the power of 11 coulomb per kg. So therefore, with these two information, we are ready to find the mass of an electron, finally. Okay, how shall we do it? So ME is what we want. I can get it by dividing this by this, right? No, the other way around. Taking this divided by this. Okay, so E divided by E over ME. That's right, then the E and E cancel, that ME here becomes inverted so that the right side is equal to the left side. Okay, so this is what we can do, and this means taking this number and dividing by this number. If you do this, you will find that the answer is 9.1 times 10 to the power minus 31 kilogram, and that is the mass of the electron.